Hi Bobcats! I'm sure you noticed in the previous video that writing some of these electron configurations gets really long. The good news is that there's a shortcut, and that's what we're going to look at in this video. Our objective is to write this shortened version, which uses the noble gases. The thought process behind writing the shortened version of the electron configuration is something like this. When the electrons are arranged in a noble gas, that particular arrangement of electrons, which would be 2 for helium or 10 for neon or 18 for argon, so on, that particular arrangement is very, very, very stable. Once we have, say, 18 electrons arranged in the pattern that they're arranged in argon, those 18 electrons are so stable they don't want to participate in chemical reactions. So the electrons that do react for an element are the ones that are past its noble gas core. So we can hide all of the electrons that are arranged in the same configuration as a noble gas's electrons by putting the element symbol in square brackets and then writing only the electrons that follow it. So, for instance, if we were to put neon in square brackets, so Ne in square brackets, that means 1s2, 2s2, 2p6, because that's the arrangement that the electrons follow in neon. Now, that's not saying that there's an atom of neon hidden within some other atom. All we're doing is saying that we have 10 electrons that are arranged in that pattern, which matches the pattern of the electrons in neon. So let's look at how we can take this long electron configuration and reduce it down to just the electrons that we're interested in for bonding purposes. Now, barium has 56 electrons. Xenon, as a noble gas, has an arrangement of 54 electrons. So out of these 56 electrons in barium's electron configuration, 54 of them aren't going to do anything. And so that only leaves 2 at the end. So we're going to want to save those 2 electrons, and then the rest of these 54 electrons we are going to cover up by writing Xe in square brackets. And so Xe in square brackets just means this long part of the electron configuration. And then past that noble gas core, we have 2 more electrons, so we'll write that 6s2. When we write the electron configuration this way, the emphasis is on the electrons in barium that are available for doing chemical reactions. There's a real quick and easy way to identify the noble gas core for an element. First, find that element that you're interested in the periodic table, and once you've found it, slide all the way over to the right where the noble gases are, and then move up 1 row. If you don't move up 1 row, you're talking about a noble gas that has more electrons than the element you want to write the configuration for. So we have to move up 1 row to get the correct element for the core. So as an example, let's find the noble gas core for selenium. Selenium is atomic number 34. It's in the P block on the 4th row of the table. So if we find selenium and we slide all the way over to the noble gases and then we move up 1 row, we find that we're at argon. So argon is the noble gas core for selenium. For strontium, well, strontium is atomic number 38, and it's way over there in the S block. And so if we slide all the way through the S block and the D block and then the P block on that row, and then we move up 1 row, we'll be at xenon. So xenon is the noble gas core for strontium. Once we've found that noble gas core, we want to write it, and then we want to add in all of the electrons that our element has beyond that noble gas core. So let's try silicon. Silicon is on the 3rd row of the table in the P block, If I slide over and go up one, I discover that its noble gas core is neon. So I'll start by writing neon. So writing that accounts for 10 electrons. I'm just going to put that down here in parentheses. Silicon has 14 electrons, so we're going to add 4 more electrons to the end of this configuration. Well, neon represents 10, so if I look for electrons 11 and 12, I find that they're in the S block, and they're on the third row of the table, so that's 3s, and we have 2 electrons in that subshell. Then electrons 13 and 14 are in the P block on the third row of the table, so I'll write 3p and then 2. And so neon, 3s2, 3p2 is our final answer for the shortened version of the electron configuration of silicon. If I write chromium's electron configuration this way, well, chromium has 24 electrons. It's in the first row of the transition metals. So if I slide all the way over and up one, I find that its noble gas core is argon. Argon has 18 electrons, so that means I'm going to have to write in an additional 6 electrons. So counting up from 18, I find 19 and 20 in the S block on the fourth row of the table, so that'll be 4s2. And then I move into the D block. Now remember, even though I'm on the fourth row of the table, with the D's we go one less. So the next subshell I'm going to use is 3D. And then if I count over in the D subshell to chromium, I count over 1, 2, 3, 4 spots. So I write down 3D4. And that is the shortened electron configuration for chromium. Argon, 4s2, 3d4. I want to give you a heads up about a possible complication that you're going to run into if you start just looking up electron configurations on the internet. If you look at the configuration for something like chromium, you're going to find a different electron configuration, very slightly different than what we just wrote on the previous slide. It turns out that there are complications in real life. So the pattern that I've been teaching you for writing electron configurations is, of course, based on a bunch of assumptions and modeling. And some of those assumptions don't hold true when we have atoms that have multiple electrons. And so really those patterns only hold true for atoms with a single electron, which would be hydrogen, or what we call hydrogen-like ions, where we have something like helium, but we've removed an electron, and so we have an He with a +1 charge. But anyway, I'm digressing. So if you're looking at experimentally determined electron configurations, you will find that there are deviations from this pattern for a number of elements. But for the purposes of this class, I want you to follow the patterns, not the exceptions. And so if you are, say, Googling an electron configuration and you submit that as the answer on a quiz, you're going to find that it's counted wrong. So make sure that the electron configurations you give me for this class are the ones that follow the patterns, not the ones that have been experimentally determined that deviate from the patterns. Our objective was to write the noble gas version of the electron configuration for atoms.